We're going to move on now to conservation of conservation of momentum. Let's consider a closed system. Remember, a closed system is a system in which a system that doesn't exchange matter with the outside of the system and on which no external forces act. So we're going to look at some collection of objects. We don't add to or take away from those objects, and only the objects impact each other, nothing outside of that. So we'll look at a closed system with just two objects in them, and let's say they interact by some force. How about gravity? So gravity is an attractive force, and they're each going to experience an equal force in opposite directions. That's Newton's third law. Let's call this object 1 and this object 2. So if I wanted to figure out, because of this force, how much the momentum of object 1 changed, the change in momentum is equal to the force, so this is for object 1, the force on object 1 times the time that force is acting. And if I wanted to find out what the change for object 2 would be, well, that'd be the force on object 2 times the time over which that force on object 2 is acting. Now, we know from Newton's third law that these two forces are going to be equal and in opposite directions, so I don't need these subscripts anymore. All I need to do is say that this one is going to be in the opposite direction as the starting one. Or I can move that negative sign over to the other side, and that'll be more convenient for my next step. So F delta t and F delta t here, those are equivalent values, so I can write that the change in momentum for object 1 is equal to the change in momentum for object 2, but negative. What does this mean? It means that when object 1 gains momentum, object 2 loses the same amount of momentum. Or when object 1 gains momentum in one direction, object 2 gains momentum in the opposite direction. So if I wanted to know what the total change in momentum is, well, it'd be the change in momentum for object 1 plus the change in momentum for object 2, which is just going to be 0. Momentum doesn't change for this closed system for the total. Now it may change for any individual object in there, but the total momentum doesn't change. Let's consider an example with this. We'll have a person who's standing on a skateboard, and he's going to jump forward off the board. And I think you probably have some intuition on this, that if he jumps forward off the board, that board is going to go flying out behind him. Now, that happens as a result of this conservation of momentum, or at least we can describe it with that. So we can express this conservation of momentum idea by saying the net, or the total momentum initial, is equal to the total momentum at some later point in time. So initially, we've got the mass of the man and the mass of the skateboard, and each one of those is going to be times their velocity. So I'll say mass of man times velocity initial for the man plus mass of the skateboard times the initial velocity for the skateboard. And on the final side, I'm going to have, well, the mass of the man again times the final velocity for the man plus the mass of the skateboard times the final velocity for the skateboard. I'm just adding up my different momentum terms. If they start at rest, I guess I didn't specify that, but we'll say that he's standing at rest on that skateboard to begin with. So this is 0, and this is 0. So our total momentum for this system is 0 initially, and that means it's got to be 0 for the total in the final state. So now we can plug in that the mass of the man is 65 kilograms. The final velocity for the man is 3.5 meters per second, and that's forward, plus the mass of the skateboard, 1 kilogram, is equal to, well, we don't know what that value is, but we can solve for it. It's the only unknown. the velocity for the skateboard in our final situation. So I'm just going to multiply the 65 times 3.5 together and subtract that to the other side, and then I'll find that I get negative 227.5 meters per second, kilogram meters per second is equal to 1 kilogram times the velocity for the skateboard, and then divide both sides by 1 kilogram to get that the final velocity for the skateboard is negative 227.5 meters per second. Now that is a shockingly fast speed, and it ought to be, because that man jumping forward, he gained a huge amount of momentum. So he went from no momentum, he was at rest, to 65 times 3.5 kilogram meters per second squared of momentum. That skateboard had to gain a large amount of momentum going the opposite direction. And since the skateboard is so much less massive than the man, the only way for it to have that momentum is to be moving really, really ridiculously fast. Like 2/3 of the speed of sound in this case. So yeah, maybe not the most realistic problem, but you see the point.